Personally, I don't like computer tests. I prefer paper.
Yeah. I think it's going the direction of more computer stuff, though.
And my eyes, like, I'm really bad vision, so looking at screens all day definitely strains it more than it already is strained.
Yeah.
But my parents said that when I qualify for LASIK, like when I'm old enough, they would pay for it. So
That's nice.
even if I'm 25, they would still pay for it.
That sounds like Daisy scary to see them have the blade and then just everything go black like that.
I don't think it's that bad. My wife had it done fairly recently, and she said there's nothing to it. And my mom had it done a long time ago when it was, I don't know, like the technology was way, way worse. Like, I'm talking like 25 years ago. And it was still fine, so.
Well, I say getting LASIK is better than having -6 in both eyes.
Oh yeah, it's worth it if you can afford it, for sure.
I already have to get a new prescription for my eyes, like every 6 months. So I can't get a
Really?
pair of glasses on that, so I just stick to contacts.
Well, LASIK may not stick forever too then. I mean, it'll last a while, but it may not last your whole life. You might have to get it redone.
That's why I'm gonna wait until I'm like older. There's less of a chance.
Okay, we've got, so we are moving on from limits, completely done with all of that kind of stuff. So, again, at the end, I think I was running out of time yesterday when y'all were finishing up your test, but especially for those of you signing up for Cali B next year, make sure you fill out that test reflection pretty detailed. Because again, that is about 80-90% of what your first unit in calculus is, but it's much quicker. It's like 2 weeks from beginning to end. So if you can quickly look back at what things you were still slow on or trying to figure out, then I think that would go a long way. But next up, or pretty much the rest of the year, it is all algebra stuff. So our next unit is really, we like to spend a good chunk of time on logarithms. Logarithms are something that most of you scale in Algebra 2, but it's usually just an introduction. I'm guessing you probably only spent like 2 weeks on it or something. And logarithms are super important, whether you're talking about college algebra or calculus. So we go real in depth with those. But before we can do that, we need to do exponential functions. So that will be section 3.1. And then before we do that, we're going to do section 1.9, which is on inverse functions. So there's a plan here. We do 1.9 this class and next, quiz in it next class, reviewing what you're supposed to know about inverse functions. Then we'll spend 1 day on exponential functions. And then we start going into logarithms. But logarithms and exponentials are inverses of each other. So if you really know what it means to be inverses of each other, and then you learn what you need to learn about exponentials, then it kind of gives you a head start on what you need to know about logarithms. So that's the reasoning there. But we will not have another test until we do sections 3.1 and 3.2 also, and then we'll have a 50-point test. Then we'll do 3.3 and 3.4, which is more logarithms, and then have another 50-point test. So all of this is kind of building up to really make sure that you understand all of what you need to know about logarithms. But today we get to just focus on inverse functions. So there's 2 steps to solve and find the inverse of a function. The first is you should switch or swap the input with the output. Now we did some inverse stuff last semester with trig. We're not really talking about trig stuff anymore. We're just doing specifically algebra stuff. But it's just that in algebra the input is usually x and the output is usually y. And then we solve for the new y, and we like to call it this. Instead of calling it f of x, it has a little -1 exponent. Just like sine and inverse sine has the thing that looks like a little -1 exponent to it. It's not really a -1 exponent, but that's what it looks like. So chances are when you learn this, and I don't know if this is Algebra 1 or Algebra 2, but you probably had teachers that just said switch x and y and then solve for y. And that's fine as long as you have x's and y's only, but you're really swapping the input and the output with the swapping input and output and then resolving it for y. So quick example of this, if I took the function and I switch x with y, there is step 1. Technically this is the inverse, but we like this to be solved for y equals. So we should maybe subtract a 1, divide the 2, and in mathematics we can't say that this is equal to y and this is equal to y because these are not the same thing. So if the function is f of x, the inverse would be written like that. That's how we keep up with which one's the function and which one's the inverse. So easy steps to apply: swap x and y, or swap input and output if it's not x's and y's, and then solve for your new y. So that's how you go about finding an inverse. Now, to prove that 2 functions are inverses of each other, there's only one way that really works all the time, the algebraic way. And to do that, you have to take one of your functions, like f of x, and you have to plug it into the other function. I'll call it g of x. So if you plug if f and g are really inverses of each other, and you plug f into g, it will simplify out to just be x. Also vice versa, if you took g and plugged it into f, it will also simplify to x. So the only algebraic way to be 100% sure that two functions are actually inverses of each other is you have to plug them into each other, simplify, and show or see that it reduces down to x. So same two functions we just did up there. Here's f, here's the inverse of f, the one we just found. So if we were to, or when you see questions like this and you were asked to prove or verify that these are actually inverses, you need to plug one of these into the other one. So everywhere there's an x, I'm instead going to put the other function. And then you need to simplify that. So it looks like times 2 divided by 2 cancels, and then minus 1 plus 1 cancels. Plugging one of them into the other and showing that it simplifies to x is half of your work, but then you actually have to show it the other direction as well. You've got to plug all of the other function into the other one, and it also has to simplify to x. So we could do minus 1 plus 1, and then times 2 divided by 2. Showing that plugging them into each other and simplifying to x is how you prove that two functions are inverses of each other. Okay, everybody done with that? Okay, if you want to know if two functions are inverses of each other graphically instead of algebraically, so this doesn't really work as a proof because it could be close but not quite. But a lot of times, like on the ACT, this would work out great. When you graph two functions, if you graph both of them, if you graph like f and his inverse, if they are really inverse functions, there will be a line of symmetry at y equals x. Again, this is not enough to prove that they're inverses, but just as a quick little snapshot, a quick look, it's about 99% safe. So, same two functions again. Now, let's say that, I don't know, let's say that this was on the ACT and you had 4 choices or 5 choices to pick out which one was the inverse, and you couldn't remember how to find the inverse algebraically, or maybe you just thought this was quicker. Maybe choice A had this written down. So what you could do is you could plug this one in your calculator, ask it to graph it. It's got a y-intercept of 1 and a slope of 2. And graph this one at the same time. You might want to split this one up, split apart your fraction. He's got a y-intercept of negative 1/2 and a slope of positive 1/2. Of course, it'd be a little bit more accurate if you threw them both in the calculator. But if these have a line of symmetry at y equals x, then it's pretty safe to assume that they're inverses. So y equals x is the line where x and y, any point on there, x and y are equal. So if y equals x looks like it's cutting your graph in half, you could flip f of x over that purple line and get its inverse, or flip the inverse over the purple line and get the black line, then it's fairly safe to assume that they're inverses. Again, it doesn't really work as a proof because it could just kind of look like it, but it could just be just a tiny bit off. So if all you were interested in is giving a yes or a no, or a way to check your answers maybe, then that's what I would do. I'd graph this, and graph y equals x. And if y equals x looks like it's cutting your graph in half, if it's a line of symmetry, then you can feel good about those being the real inverses of each other. Okay, so other stuff we talked about, does most of this, did y'all do this in Algebra 2? Review this at all in Algebra 2? Even like graphing part? Not that part? Okay. Okay, and then to finish up, a couple more things we need to remember is that there is a thing called a vertical line test. And if a relation passes the vertical line test, that tells you that it is a function. If something passes the horizontal line test, it tells you, I don't like the wording of this, that the function has an inverse that is a function. So you don't have to remember this from last semester, but when we did inverse trig functions last semester, we had to restrict a lot of the domains to make sure that they passed the horizontal line test to ensure that their inverse was a function as well. So that's why we had to go through all those hoops. We do need to squeeze this in right here. There is a term that will come up that also comes up on the ACT. You need to know what it means to be 1-to-1. To be 1-to-1 means it passes both the vertical line test and the horizontal line test. It's a function and its inverse is a function. It's a function because it passes a vertical line test, and then it's its inverse is a function if it passes the horizontal line test. If it does both, we say it's 1-to-1. Just the vocab term. Okay, and then last connection I need to make for you on here is the way that functions and their inverses, the way the points are going to relate to each other. So let's say I don't know, let's just pick out a couple points here. Let's make up a quick example. Let's say some function had the point like 0, 0, 1, 4, and I don't know, -2, -3. I don't know, doesn't matter too much. Well, if we are given those points about a function or its inverse, we should be able to give points of the other one, because all it means to be an inverse function is you're swapping input and output, or you're swapping x and y. So if I swap x and y here, 0, 0 stays 0, 0, but 1, 4 becomes 4, 1. -2, -3 becomes -3, -2. And even though I only made up 3 points here, notice because I drew them and visualized it, notice how these have a line of symmetry at y equals x. Y equals x cuts the overall, well, my graph is kind of bad, but it's supposed to cut the overall shape in half. So you need to understand that if you're given some points, how to name some points of the inverse. And all it is switching x and y, because that's all inverse means. Now, last part I need you to put on here is the one other thing that's going to come up on the other handout that I want you to try on your own before we go over it. But you need to make this connection between domain and range. The domain of a function ends up being the, when you switch x and y, it ends up being the range of its inverse. Possible x's become possible y's, and the range of the function ends up becoming the domain of his inverse. Possible y's become possible x's. Again, if you're just switching X and Y, then you're switching possible X and possible Y. Domain becomes range, range becomes domain. Okay, so next up, you've got the other handout that I'd like you to do as a quick little practice quiz. So without your notes, go ahead and try these and see how it goes, and we will go over it. So any of them you don't know how to do or any of them you make a mistake on, we'll correct it and learn from that. So you don't need to feel like you need to lean on your notes. You just need to see what, from that quick little reminder, what you actually know so that you can narrow down what it is you need to learn or relearn. say like 5 minutes to try to be finished. And then we'll go over it. Also, before I forget, a reminder about the ACTM if you're interested in doing that. I know that there seems to be a little bit more interest this year because Mu Alpha Theta is offering some hours if you do it. But if you want to sign up, that would be great, but you have to let me know you're interested in doing it, and you have to pay your $5, and I need that by the end of next week at the latest. There's a process of getting it to the right person on campus, and then they've got to turn that into a check, and then that's got to be sent over to the university. So if you don't make the right deadline, then there's nothing I can do to squeeze you in at the last minute. It'll be out of my hands. So if you know that's something you're interested in doing, you need to put it down in your planner to get your $5 to me as soon as possible. As long as I get it anytime next week, it will be fine. I had mentioned the ACTM in here before, right? Okay, just making sure. And there's lots of practice tests on my website if you want to see what they've been like in the past. it's been 5 minutes, so let's go ahead and check your answers and help you fill in the gaps. This is the close to what the quiz will look like. And again, our quiz is next class. This is just very quick to the point. So this should help you identify which questions you need to look back at. Now, my guess is that most of you probably got question number 1 right. But again, just be careful. If you're getting it right because we just talked about it and you don't think about it again between now until next Tuesday, then I guess you could miss it on the quiz. So you might still want to review it. But basically, if you've got a bunch of points on a function, you should be able to give a bunch of points on the inverse, because inverse just means you're swapping input with output, which in our case means switching x and y. And that's it. Questions about number 1? Okay, question 2 then says to verify that these two are actually inverse functions, and it even goes further and gives you a hint here, although we certainly don't need to give you this. You're not supposed to need this hint. The only way to prove or to verify that two functions are inverses of each other is to take one of them and plug it into the other one. So instead of 4x minus 12, you're going to put the entire function in for x, and instead of 1/4 x plus 3, you're going to plug the entire function into that. And you do have to go both ways. Doing one way is not sufficient, even though there's very few, if any, algebra functions that I know of that would work one way but not the other, but it's still important that you do both. And you need to simplify these. If you distribute the 4 and combine your like terms, versus if you distribute your 1/4 and combine your like terms, if they're really inverse functions, both ways should simplify out to x. So if and when we ask you to do this on the quiz, that's what we're looking for. Did you plug one into each other and show that they simplify to x? There you go. What's this? It was extra. Okay, 2. Okay. Question 3. So this is about knowing what it means to be one-to-one. So to be one-to-one, you should have come up, and again, your answer is going to look different than mine, but it has to pass the vertical line test. So like this does not pass the vertical line test because I can draw any vertical line that hits my graph more than once. So you could try something like this that passes the vertical line test, but to also be one-to-one, it also has to pass the horizontal line test, and this does not pass the horizontal line test. So this works for this, but not for this. Oh, and that's what I wanted. Never mind. I thought it said is one-to-one. So there's one example. It's a function because it passes the vertical line test, but it's not one-to-one because it did not pass the horizontal line test. And obviously your graph doesn't have to be the same as mine. Okay, and then a function that is one-to-one, so you need to come up with one that does pass the vertical line test, like maybe that. But to be one-to-one, it also has to pass the horizontal line test, so this does not work. But I don't know, try not to overcomplicate it. This passes vertical and horizontal line test, which is all it means to be one-to-one. It doesn't have to be a fancy function. It just needs to be a function, pass the vertical line test, and one-to-one, pass the horizontal line test, not one-to-one, not pass the horizontal line test. Okay, we good with that one? Okay. Alright, question 4 wants us to find the inverse of this. So this is the first thing we did in the notes. And it even gave us some steps here, but you need to make sure that you can do this without the steps. because the steps are just swap input with output, and then solve for y. And then the only thing that's it seems a little bit picky, but it is important in math. Remember, f of x is the same thing as y. Y can't be x squared minus 1 and the square root of x plus 1. Those are not equal. So you can't say y is equal to both of those. So this last part where it says replace it with inverse notation, you should say that is the inverse of f. Okay, we've got I'm not really sure why we did this. See if it comes to me, but t-chart for f of x. So if I plugged in these values into f of x, you plug in 0 and solve, you get -1. You plug in 1 and solve, you get 0. You plug in 2 and solve, you get 3. I think that maybe helps some people with this. I don't know. I don't really see it. But if I want to know what's the domain of this, I've got two ways to do this, and both are fine. I would suggest that you try to do both for consistency. When I look at f up here, I'm thinking about his domain and his range. His domain has been restricted. They tell me what it is, the x values that it can be. His range, well, to get range, you've got to think about what this graph looks like. We all know what x squared looks like. So if we shift it down 1, what would the range be? Range would be from what to what? -1 to infinity. Smallest y value, and it hits it, so bracket the biggest y value. And if I know that about the function, now again, you do have to put some thought into what the range is, then domain and range just switch for his inverse. Possible y's become possible x's, and possible x's become possible y's. And this is like 0 to infinity, if you'd rather look at it in interval notation. So they wanted this guy, which was -1 to infinity. That's option 1. Option 2 is you should have the inverse from right here, and you could think about what numbers you could plug into this, and or you could think about what this graph looks like. The square root of x looks like this. This is going to shift it left 1. So the x values that he hits is -1 to infinity, but just a second way to find the same answer. All of that is interconnected. Okay, questions about number 4? Did anybody get this part right? No? Okay. All right, so you might want to write down in some words those two methods when we finish here so that you have something good to look at. All right, question 5 is a lot of a repeat of question 1 in my opinion. If you have some points on a function or some points on an inverse, switch x and y and you've got points on the other one. Let's come back to number 6 because number 6 is definitely the trickiest. Number 7, the graph of a function must pass the blank line test. Well, if it's a function, it's got to be the vertical line test. Vertical line test tells you that it's a function. If the graph of a function also passes the horizontal line test, then its inverse is a function. If it passes both the vertical line test and the horizontal line test, that is called one-to-one. It is a one-to-one function. Okay, so question 6, I'd say the most common answer here is going to be not possible, but it certainly is possible. So the path you needed to take here is, first off, it needs to be a function. So whatever you draw needs to pass the vertical line test. So if you have an answer that does not pass the vertical line test, that cannot work. 2, it needs to be an odd function. Well, just like with trig functions, odd functions means that it has symmetry to the origin, which is like the same thing as or rotating halfway around. So this is not an odd function. I can't turn my paper upside down, but if you take your paper and turn it upside down, if your graph looks the same after you turn it as before you turn it, then that is an odd function. The most common odd function is x cubed. That graph looks the same whether it's like this or if you turn it upside down. That's the definition of an odd function. So you have to come up with something that's odd that does not have an inverse function. So he has to be a function, so he needs to pass the vertical line test. But to not have his inverse be a function, you needed to fail the horizontal line test. So even though x cubed is close, x cubed is not correct, because x cubed has an inverse function. He passes the vertical and horizontal line test. So what you could do is you have to think of something that meets this requirement. It's the same frontwards as upside down that breaks this, that would not be passing the horizontal line test. So one little change here. If you make this have a little bit of a bump, now it's a function. It's an odd function because it has symmetry with respect to the origin. It looks the same way this way as it does upside down. And I know his inverse doesn't have a function because what I drew did not pass the horizontal line test. So that one's tough because you have to kind of do a little bit of guess and check, and you have to know what all those things mean. You have to remember what an odd function is. You have to know what has to be true to make it a function. You have to know what has to not be true to make sure its inverse is not a function. And if you don't play with it long enough, then usually students give up too quickly and say not possible. But your quiz could have one similar to that. So scan through here and see if there's any of these you'd like me to talk about again, or any specific questions you'd like to ask. This is the stuff that you need to feel solid about on Tuesday for the quiz. And while I give you a second to look that over, I am going to take up this one for homework grade, so I'll go ahead and put it in Google Classroom right now so I don't forget this time. Number 80. Alright, I already opened that up in Google Classroom, so if you want to turn it in there so that you don't have to worry about it next week, then please do. Any questions, anything jumping out at y'all on this that I can help with?
Here's my homework from the day I missed.
Okay. None of these you need me to go back over? Okay. So as I mentioned when we started this semester, a lot of our algebra stuff is like this. It's usually pretty short and sweet. If you remember some of it or most of it from Algebra 2, then it's usually fairly easy. If you've forgotten it or you never learned it, it is often kind of quick because you know, we're just not going to, we can't afford to spend, you know, a full week on this. So, one full class period, give you a chance to ask questions and study, and then we'll quickly quiz on this next class and then move on. Okay, I'm going to turn the screen off here in a minute, but if you guys do find any questions, then please ask before you leave. I would suggest you write down about your quiz on Tuesday somewhere to remind yourself. And you may want to make some notes about what it is that you think you might forget. But otherwise, that's all I've got for you. And you guys have got about 30 minutes. So.